In this video, I want to expand a little bit on the difference between mass and weight and the force of gravity and the normal force, and how we can use all of these in calculations, how we actually find numeric values for some of these forces. So we're going to do some example problems. In an earlier video, I suggested that the word weight can be problematic, and we'll actually take a little bit of a look in this video at why it can be, and then we'll talk a lot more about it in a future chapter. In the meantime, if you say an object's weight is the force of gravity of the Earth pulling down on the object, that is actually how most scientists would define it, and for now that'll be perfectly fine. Again, I'll keep avoiding the term because of reasons that I'll explain later, and I'll say it's the object's gravitational attraction to the Earth, or the force of gravity pulling down on the object. So let's take a look at how to calculate the force of gravity pulling down on any object. It's this equation right here. The object's mass in kilograms times the gravitational field strength of whatever planet you happen to be on. And we'll just assume we're on Earth in any problem where it doesn't say otherwise. So for example, this jet has a mass of 240,000 kilograms. That means that its gravitational force is 240,000 kilograms times the gravitational field strength. And on Earth, that's 9.8 newtons per kilogram. 9.8 is a really conveniently familiar number. 9.8 meters per second is the gravitational acceleration if you drop an object. And if you do a little bit of playing around with the units, you can prove that newtons per kilogram is equivalent to meters per second. So a lot of times people will just say that the mass times the gravitational acceleration is the force of gravity, and that fits with the structure of F equals ma. So you can do that, and it'll work out just fine. The force of gravity then on this jet would be a little bit over 2.5 million newtons, which is probably not a really useful number for you, because newtons, what is a newton anyway? So that I would understand what 2,532,000 of them is. I do want to give you some sense of what 2.5 million newtons is. It's about 265 tons. This is really only here to emphasize that the unit of force is newtons, and I do not expect you to know how much a newton really is in an everyday sense. Throughout the sense of this course, and also if you're taking the 140L lab, you may start to get a sense of what's a lot of force and what's not so much force in newtons. But in the meantime, it would be helpful if we had a couple examples coming up that would give you a better sense of what's a lot of newtons and what's not. This first example, this should look really familiar also. We had the free body diagram that we drew in the previous video. We had this book on the table, and I'm pulling up on the string, and here's our free body diagram, and we're going to do a calculation now. This is a pretty typical intro physics question. If the book has a mass of 0.7 kilograms and the string has a tension of 2 newtons, what's the magnitude of force between the table and the book? So if I didn't already do this, I would start out with a quick sketch to make sure that I had an idea of what was happening in this problem, but they gave me a picture, so I don't need to do that. If I didn't already have a free body diagram, I would go ahead and draw one now so that I understood all the forces that are acting and in what direction. Are they helping each other, or are they working against each other? And here I have them already drawn, so that's pretty convenient. So where do I actually start doing calculations? I'm going to start with the fact that the force of gravity is the mass of the book times g, the gravitational field strength or the gravitational acceleration. That is how strong the force of gravity vector is that we have drawn on the free body diagram. Our goal with the free body diagram is to draw all of these forces in the directions that we know that they're acting, so we can identify what they all are. But the next step of it is to start doing calculations with as many of them as possible to help us solve for the ones that we don't know. So the force of gravity pulling down on this book is the 0.7 kilograms times 9.8 newtons per kilogram, and that gives me 6.86 newtons downward. I'm mentioning downward here because when we go to do some math, what we're going to find is downward is a negative y direction. We're going to have to refer to this as 6.86 newtons negative when we go to do the math. The math that we want to do is actually this. The net force acting on the book is equal to the mass times the acceleration. And since the acceleration of the book is 0 because it's stationary, then that means the net force acting on this book is 0, which means the upward force of the string plus the upward force of the table on this book minus the force of gravity, and I'm saying minus because the force of gravity is pointed downward. Those three are the three forces that are acting on the book, and when I add them together in this format of string up positive, table up positive, gravity down negative, they will equal 0. If the book were accelerating, they wouldn't equal 0, they would equal ma, but that's not the case. They equal 0. The net force is 0. The string is pulling up with 2 newtons, they told me in the problem. The force of the table, I don't know how much it is, but I know it's plus because it's pointed up. And the force of gravity is negative because it's pointed down. That's where the negative comes from, is I know it's pointed in the negative y direction. So all I have to do now is solve for force of the table. That's pretty straightforward. It's 4.86 newtons. That's the force of the table on the book. That's not too bad, right? Let's try one of the other questions that we had a free body diagram of and make sure we can calculate the same type of thing here. In this question, we want to know if the book has the mass of 0.7 kilograms and I push with a force of 14 newtons, what is the magnitude of the force between the table and the book? I'm sorry that the free body diagram and the words are kind of bleeding over each other there. I hope you can make out what it's saying. I'm going to start the same way as I did last time. I have these 3 forces drawn on this free body diagram. I'm given that the downward force is 14 newtons. That's the hand pushing down. I'm not given either of the other 2, but I'm given enough to find the force of gravity, mass times g. The mass is 0.7 kilograms. G is 9.8 newtons per kilogram. That's 6.86 newtons downward. I now have 2 of the forces on my free body diagram, so I can say that there's a way to relate these 2 forces to the force of the table, and that is Newton's second law. F net equals ma. Again, in this case, the acceleration is 0, so the left side of this equation, F equals ma, must also be 0. The net force that will be equal to 0, what is the net force? It's the vector sum of all of the forces acting here. That's the force of the hand, which is negative because it's pointed down, plus the force of the table, plus because it's pointed up, minus the force of gravity, minus because it's pointed down. I put in my numbers for the net force equals 0, the force of the hand is 14 newtons, and the force of gravity is 6.86 newtons. And now I solve for the force of the table. The force of the table pushing up on the book must be 28.86 newtons. It must be strong enough to hold up the book, plus strong enough to counteract the pushing force of the hand. Let's take a look at a slightly more complicated one because, again, I'm sure that you're looking at this and saying, I hope he makes it more complicated. Here the question is, what is the magnitude of force between the table and the lower book? The lower book's mass is 0.7 kilograms, but the upper book is now given as 2.2 kilograms. Well, initially, I don't know that I care about the upper book. I'm going to start with the lower book because that's what they're asking about. I'm going to analyze that lower book first, and I'm going to say the net force acting on the lower book is equal to ma. I'm going to put some subscripts in just because I know that I'm going to have to use F equals ma later. But if you didn't know that and you just wrote F equals ma to start, that's fine. You can always go back and put subscripts in later when you need them. The acceleration of the book is 0, so F net, which will be equal to 0, equals the vector sum of the various forces acting on the lower book. That is the force of the table on the lower book pointed upward, the force of the upper book exerted on the lower book pointed downward, and then the force of the Earth's gravity on the lower book also pointed downward. So that's why the upper book acting on the lower book and the Earth's gravity acting on the lower book are both given negatives in this equation. 0 net force because the lower book is not accelerating anywhere. So that equals the force of the table on the lower book minus the force of the upper book on the lower book minus 6.86 newtons, which is the gravitational attraction of the Earth on the lower book. I can't solve this yet for the force of the table acting on the lower book because I don't know what the force of the upper book on the lower book is. Well, I'm stuck then. Maybe if I investigate what's going on with that upper book, I'll know how hard it is pushing down on the lower book. So now I analyze that upper book. I see from the free body diagram there's just two forces acting on the upper book. I know Newton's second law says that the net force acting on the upper book equals the mass of the upper book times the acceleration of the upper book. And I know conveniently that the acceleration of the upper book is 0. Again, if it wasn't 0, but it was some known value, we could still make this work. The net force is the vector sum of all the forces, and we only have these two forces that are acting in the y direction, so I can just add them together, keeping track of which ones are positive and which ones are negative. So I have the force of the lower book pushing up on the upper book minus the force of gravity pulling down on the upper book. That equals the net force. And the net force is 0, so I put in the mass of the upper book times the gravitational acceleration due to gravity, or the gravitational field strength, the 9.8 newtons per kilogram. Please note, I'm not putting in negative 9.8. And the reason I'm not putting in negative 9.8 is because I've already said this is a negative force when I said minus force of gravity on the upper book. So don't double negative yourself by putting it in more than once. I solve this and say that the force of the lower book holding up the upper book must be 21.56 newtons, because that's how much the Earth's gravity is pulling the upper book down. The lower book has to push up that much to hold it stationary. Well, if the lower book is pushing it up that much, that's how much the upper book is actually pushing down on the lower book. Let me be really, really clear about this. Newton's third law says that any force you have on a free body diagram will appear in the exact opposite direction on a different free body diagram. So the force of the lower book on the upper book is equal to the force of the upper book on the lower book. In fact, it's not even that they're equal, it's that that is the same interaction. It's just felt in opposite directions by the two different objects. If I were drawing a free body diagram for the table, this force would appear on the table's free body diagram pointed downward. If I were drawing a free body diagram of the Earth, then this force and this force, the two red vectors, would appear on that free body diagram pointed upward, because that's how Newton's third law works. It is a connection between any two free body diagrams. So what that means is if this force right here was calculated to be 21.56 newtons, then this force is also 21.56 newtons. Should I make this one 21.56 newtons negative when I put it in? No, because I've already taken care of the fact that it's pointed downward when I put this negative sign in right here in my net force equation. You only want to put it in once. So now I get back over to the lower book and I say the force of the table on the lower book, which is what I'm trying to find, is equal to the force of the upper book on the lower book plus 6.86 newtons. That 21.56 newtons substitutes in very nicely, and I get that the table has to put an upward force, a positive force, of 28.42 newtons on the lower book in order to hold that lower book up. I hope that wasn't too bad. Let's take a look at another example here. Do you always need a free body diagram for every force problem? And the answer I'm going to give you is, it's never inappropriate, but it's not always necessary. If you don't include it, then it's sometimes harder for me to tell what you were trying to do, and that especially matters if you don't get exactly the right answer. But in a question like this one, a 2.5 kilogram lab cart, a 1 Newton unbalanced force in the positive direction for 3 seconds, what's its final velocity? The initial velocity was 5 meters per second in the negative direction. You might think you're comfortable just jumping straight into the equations, and I'm not going to get upset with that unless you were specifically told that you needed to draw a free body diagram. Especially if a problem is only acting in one dimension, which is what this one's doing. There are forces in the y direction on this cart, but a force pushing in the x direction is what's causing it to accelerate in the x direction. This is one that you would draw a free body diagram if it seems useful. I would certainly still at least draw a little bit of a sketch. I would then list my givens. And this can help me figure out what equation I'm looking for to help find my V final that it's asking for. I would go with this. The force times delta T equals the mass times delta V, and I know delta V is V final minus V initial, so I can say that the force times delta T equals the mass times V final minus V initial. And if you look at that equation right there, I have the force, I have the delta T, I have the mass, and I have the V initial. I can rearrange all this to solve for V final, plug in my numbers, be very careful to keep my negative 5 meters per second, and I get a V final of 3.8 meters per second in the negative direction. So we slowed this cart down. It was moving in the negative direction. We applied a force in the positive direction. That slowed the cart down. Okay, I'd like to give you an example with an elevator. This is also one-dimensional, but now the one-dimensional is Y instead of X. Here we have a 75 kilogram man standing on a scale in an elevator. What does the scale read when the elevator is at rest? One of the reasons that I avoid the word weight is because how you weigh something is you put someone on a scale, you put the object or person that you're weighing on a scale, and you see what the scale reads. In a problem like this, the scale will read the upward force necessary to hold this person from falling. Don't ask why we have a scale in an elevator. That's a very physicist thing to do. The question is, what does the scale read when the elevator's at rest? And then also, second question, what is his acceleration when the scale reads 762.0 newtons? So our free body diagram is actually given to us. We have the force of gravity pulling down and the force normal pushing up. I know it's a normal force because it's a contact force between our 75 kilogram man and the scale that he's standing on. So to solve that first question, I'm going to go to Newton's laws. Newton's second law is our relation over and over and over again, our relation between the net force and the kinematics of the object that we're talking about, in this case, the man. When the elevator is at rest, the man is at rest. He's just standing there. So his acceleration is 0. The net force is all of the forces acting on him. That is the normal force pointed up and the gravitational force pointed down. So the normal force pointed up minus gravitational force pointed down equals ma. By the way, this is a great place to point out, if you didn't call it the normal force and you called it the force of the scale, there's nothing wrong with that. That would be perfectly fine. Rearranging this for the normal force, I get that the normal force is equal to ma plus the force of gravity, mg. And I've separated it out like this, m times a plus g. The reason I've written it like this is that this is true for elevators over and over again. In this case, the normal force is 75 kilograms. His acceleration is 0. Gravitational field strength is 9.8 newtons per kilogram. Let me again be clear. Why is this positive instead of negative? I thought 9.8 was negative, you might be saying. Yeah, but the negative means downward. If you drop an object, it accelerates 9.8 meters per second downward. The negative means that. You've already said right here, or at least I have, that the force of gravity is acting downward. That's what that negative means. You say it once per problem. You don't say it more than once per problem. So this man weighs 735 newtons. A 75 kilogram man is a pretty average size man. That's someone in the 160 pound range. So if someone weighs 160, 165 pounds, which is probably a good estimate for Albert Einstein here, that's about 735 newtons. That's just to give you an idea of how much a newton is. Let's do the follow-up to that question. What will his acceleration be when the scale reads 762 newtons? Hang on, is that different from what it said earlier? Yeah, when it was stationary, he weighed, or the scale said, 735 newtons. Now it reads more because the elevator is accelerating? Yeah, absolutely. The net force on him is equal to ma, and the net force is the normal force pushing up and the gravitational force pulling down. The scale's holding him up, the Earth's trying to pull him down. This equation is still true, and this equation is still true. In an elevator, the normal force is equal to the mass of the object times the quantity, acceleration plus g. In this step, I'm looking for the acceleration of this person. So I put in all the things I know. The scale reads 762 newtons, his mass is 75.0 kilograms, and the gravitational field strength is 9.8 newtons per kilogram. Then I solve for A. The acceleration is 0.36 meters per second squared. I want to point out to you, the acceleration should come out to be positive if the scale reads more than it usually would. When you are standing on a scale in an elevator, it reads what your weight is, what the force of gravity is pulling down on you. But the scale, when you go to weigh yourself, will read more if you are in an elevator that's accelerating upward, because the elevator has to provide enough force to hold you steady plus a little bit extra to accelerate you upward. In order to accelerate you downward, the scale would then read less. It's applying enough upward force to almost hold you stationary. So it would actually read a negative, it would give a negative acceleration if the scale read less than usual. There's an example in the textbook where it talks about the same thing. It's actually a different 75 kilogram man here. And I told you a scale in an elevator is a pretty standard physicist thing to do, so you'll see these examples in several places. Their question is, calculate the scale reading if the elevator accelerates upward at 1.2 meters per second squared. And I start right out with this equation right here. You can start with F equals ma and then say the net force is the normal force pointed upward and the gravitational force downward, and derive this equation every time. If you start an elevator question with this equation right here off the bat, that's fine too. I'll know where it came from. The scale reading of his mass times the acceleration plus the gravitational field strength. And notice I'm adding meters per second squared to newtons per kilogram. That's because I told you earlier those are actually equivalent units. The normal force is then 825 newtons. So this reads even more than it did in the previous problems because the elevator is accelerating upwards even more than it had in the previous problem. In part B, calculate the scale reading if the elevator moves upward at a constant speed of 1 meter per second. If it's moving upward at a constant speed of 1 meter per second, what is the acceleration? I'm going to go with 0. Constant speed of 1 meter per second means there is 0 acceleration. It is not changing its velocity at all. So if you're moving upward or downward or sideways at a constant velocity, you're not accelerating. And so in the elevator, the scale would read the exact same as it would if it was stationary. Remember, stationary means you're at a constant velocity. It's just that your constant velocity happens to be 0. At any constant velocity, the scale would read the same amount as if you were stationary. That's why when you get in an elevator and you feel a little bit of a sensation in your stomach or in your knees, when you accelerate upward and when you accelerate downward at the beginning and the end of the ride, that's where you're feeling it. But especially on a long elevator ride, you can feel that for a large part of the ride, it just feels like normal. You're just standing around. If you don't remember where that acceleration of 0 came from, we go back to our conversation about the definition of acceleration, which is the slope of a velocity versus time graph. And we initially had this question about an elevator that accelerates upward for the first 3 seconds, and then it accelerated downward for the last 5 seconds or so to bring itself to a stop. The acceleration from 3 seconds to 18 seconds is the slope of this graph. That's 0. There's no change of velocity. It's not accelerating. Because a scale in an elevator will read your mass times your acceleration plus g, I want to point out what happens in the horrible situation that the cable breaks. Far over on the right here it says, if the cable breaks, 0 weight. That's a funny way of defining weight. The weight, if it means the force of gravity, then the weight is still there. She still has mass. The Earth still has mass. There's definitely a force of gravity. But if you try to weigh her by putting her on a scale, it's going to say 0 because this poor girl and her scale are both free falling at 9.8 meters per second per second. If the cable breaks and you're in free fall, your acceleration is 9.8 meters per second downward. So you would have negative 9.8 plus 9.8. You'd have 0 times the mass. So the normal force is 0. And if you think about what the normal force is, that's the contact force you're making with the scale or the ground or whatever it is that's holding you up from falling. The whole point was that's gone away because the elevator's falling. Nothing's holding you up and you're falling. So this equation is valid each time you're in an elevator, whether you're accelerating up, accelerating down, or accelerating not at all. All right, that's it for the examples in this video.